In our last video, we took a look at whether or not a reaction would be spontaneous or not, and we also took a look at reaction rates. Today we're going to look at something a little bit different. We're going to look at molecular collisions. So let's briefly describe this. And it's pretty simple. In order for a reaction to occur, chemicals have to collide. So let's write this down. Molecules or atoms must collide. So basically, you've got these little atoms or molecules kind of zipping around, and when they bump into one another, a reaction can occur if the conditions are right. I did want to put a little asterisk here because there is an exception. So the exception is going to be decomposition reactions, where one molecule just falls apart on its own. All right, but for all other reactions, we do need to think about them essentially bumping into one another. And what chemists are really interested in is kind of the sequence of events. So is it just one collision or is it a multi-step process? And this is called a reaction mechanism. Chemists are obsessed with figuring out the details of these reactions involving studying these reaction mechanisms. And so this is just going to be a detailed description of what takes place. And it's interesting, right? You can't just go around, saying, I think this. You have to support it with data. So really, you have to be clever, come up with a bunch of experiments to support your proposed reaction mechanism. But the weird thing is, we can never prove anything. The joke is that you do proofs in math. You don't do proofs in chemistry, right? You support things with data in science. So this is what a lot of scientists will work on. All right, so let's take a look at some basic assumptions for a chemical reaction. All right, so number one, it's pretty straightforward. It basically says that particles must collide. That's kind of what I said before. For a reaction to occur. But like I said, we're going to put a little asterisk here because we know that decomposition reactions don't really fall into this. All right? And then number two, the collision must have a minimum amount of energy. If there's not enough energy, really the reaction's not going to occur. They're just going to glance off of one another. So it needs to have a minimum amount of, let's put total energy in here, and I'll actually describe what that is here in a second. All right, and then number three fits more into my field, which is organic chemistry, but it says that some reactions, not all of them, but some reactions require a collision with a specific orientation. Meaning they must hit each other kind of with the appropriate sides hitting one another. Oops, sorry, I kind of spelled that wrong. I'm sure you notice a lot of my spelling mistakes here, and I apologize for that. It's hard to write and talk sometimes. All right, so these are going to be the basic assumptions that we'll be using when we're discussing all of these. And there's some more things we can occur. So I want to go back to number two here, where it talks about the total energy. And we can make some, in general, observations. All right, so let's compare if we have a solid versus a liquid versus a gas. Well, which of these has the most total energy that would allow for collisions to occur with higher energy. Well, what I would do is I'd say, well, gases we know have more molecular movement. So I would just write this here. So more particle movement. They're going to be zipping around at much faster rates, which in turn means that these will have faster reaction rates, right? So solids typically have slower reaction rates. In fact, if you think about a reaction occurring at a solid, so let's say you've got a piece of iron out, it's going to occur really slowly because it's really only going to react with oxygen on the outside of the solid, right? The interior of the iron is essentially going to be inert because it's not going to be exposed to any oxygen molecules. So that is a big thing that we need to consider. All right, but chemists are always interested in figuring out how to increase reaction rates because we don't want to wait around for millennia. So there's a bunch of different things we can do, and we'll take a look at a basic one first. So how can we increase reaction rates? All right, so there's a really simple tool, and it's simply apply heat. To increase total energy. All right, and I wanted to kind of break this down because total energy is broken into two parts. First, it's going to be made up of kinetic energy. That's basically, the molecules or atoms zipping around. But we also have something called internal energy. Let me actually slide this all over a little bit. But internal energy basically describes the energy associated with vibrations. Or even atomic vibrations down to a certain level. So a good way of describing this is, let's imagine that we have a little water molecule, right? If we heat up this water molecule, these little arms could almost act like rockers and they could vibrate back and forth. In addition, they can almost act like springs and go in and out. But that gives us more internal energy when we vibrate the bonds within molecules, which is kind of interesting. So this total energy is important. That allows us to have enough energy for the reaction to occur, but it's not just the kinetic energy, which is important to remember. All right? So keep this in mind, that there's more to internal energy or total energy than meets the eye here. Okay, so that leads me to my next part, is that reactions have to overcome something called an activation energy. An activation energy is essentially like this energetic barrier preventing a reaction from occurring. So you got to nudge it over that barrier. So we have to overcome activation energy for it to occur spontaneously. All right, so this requires an initial nudge of energy. All right, so let's break this down. And if you remember, in the previous video, I gave us an example of a reaction going spontaneously from A to B, right? And we said we could look at this in terms of an energetic landscape. This is called our energy diagram. And I said one thing that really bugged me in the book was they didn't really do a good job of describing the energy we're looking at. We measure it in Gibbs free energy. That tells us the energy available to do work. Okay, so I know it's a lot of kind of nitty-gritty terms here, But if the reaction's spontaneous, that means that we're going from some starting material A down to some product B that is going to be lower in energy, right? That's why it's spontaneous, is it wants to go to a lower energy state. And we said in our previous video that essentially we could measure this difference to determine if a reaction's spontaneous, right? So over here we could say that this is our delta G, and in this case it is negative, which means that the reaction is spontaneous. All right, but this isn't the full story. Like I said up above, reactions need to overcome an initial energetic barrier in order to occur. So what ends up happening is you have some sort of energy profile that looks like this. And what we have right here is this initial hump that we have to overcome. This initial hump is called the activation energy. So you can imagine, let's imagine we're stuck in this little well right here. If we don't have enough energy to get over this hill, the reaction's not going to be, it's not going to even occur, right? We have to have enough total Gibbs-free energy available to actually crest that hill, and then the reaction will be spontaneous. So it is important to remember that we have this energetic barrier. But that leads me to my next point, that not all energetic barriers are created equal. Some are really large and some are really small. And in fact, I've got a good example down here, and I'm going to pull this from the book. It's just easier to copy this over. So let's take a look at this image from the book, and they compare two different reactions. Okay, on the left, let's write down this reaction. If you take phosphorus, specifically, it's going to be a 4 to 5 ratio of phosphorus to oxygen, and you react it, you can make tetraphosphorus decoxide, which is P4O10. This stuff is really nasty. If any of you are veterans and have ever done nighttime training, the incendiary mortar shells that they fire are usually white phosphorus rounds, and this gives off an incredible amount of light, but it's pretty hazardous to work with. You don't want to get any of the byproducts on you because it can actually give you terrible chemical burns. All right, so if we look at this reaction, it has a really low energetic barrier. And in fact, this reaction will occur spontaneously at 34 degrees because it has such a low barrier, right? So this occurs even in a really hot room spontaneously, right? So it's something you have to be careful with, especially if you're going to be storing these munitions in some sort of, let's say, open container that's sitting in the sun all day. All right. On the other hand, we've got this other reaction over here. This is sulfur reacting with oxygen. This will react and it will form sulfur dioxide, but this time the activation energy is going to be a heck of a lot bigger, right? So both of these are spontaneous reactions, right? So both of these we can tell have a negative delta G because our products are more stable, but the one on the right has a much bigger hill to overcome. So we could imagine that this will require a higher amount of temperature in order to take place, and that's exactly true. In fact, if you test this reaction will not occur spontaneously until it is at 232 degrees Celsius, which means it needs a much higher nudge to get over that initial activation barrier. All right, I hope that makes sense. This is kind of the quick and simple view of this. There's a heck of a lot more math behind this, but we aren't going to cover that in this course. All right, and I did want to finish up by talking about one important thing that I mentioned in part 3. And this gets us into a little bit of organic chemistry, but bear with me. And this says that for some reactions, orientation of collision matters. Not all of them. So for example, if we had spherical atoms, one side of a sphere is the exact same as another side of a sphere. So it doesn't matter when individual atoms react, but rather when molecules react. So let's take an example. All right, so let's imagine this molecule right here, where we've got carbon bonded to 3 hydrogens and an iodine coming off. This is iodomethane. And let's imagine that we have hydroxide, which is an anion right here. Well, if hydroxide tries to react here, nothing's going to happen because it's attacking from the wrong side. So let's just write this down. We'd say no reaction if OH minus attacks the same side as iodine. All right, so then the question is, well, what's better then? Well, in this reaction, it prefers to attack the back side, meaning it's going to attack the side with the hydrogens, meaning the opposite side of the iodine. And when this happens, it's almost like playing a billiards game, right? So this is going to attack the carbon from the backside, thereby kicking the iodine off the other side. And it's kind of a neat reaction. This is called an SN2 reaction. It's a substitution reaction because we're kicking one group off. Specifically, we're kicking off that iodide. So in this case, we can see that the OH minus must attack from the opposite face of the iodine. The book doesn't get into this in much detail. I just want you to know that this is really important for some types of reactions, but not all reactions. So like I said, if you've got two spheres reacting, one side of a sphere is the exact same as another, so it doesn't matter. This only matters for molecules where you've got one face that's different from another. All right, I hope that helps, but let me know if you have any questions.